Section 12.2 defines a new geometric and algebraic object, which we will use throughout this course. We will define an object called a vector. We will see where vectors appear in the real world. And finally, we will learn a few mathematical operations that can be performed with vectors. The first thing to ask when encountering a new mathematical object is how to define it, and what we can measure about it. A vector is a mathematical object that consists of both a magnitude, or a length, and a direction. It models a displacement, that is a change between positions of 2 points. With a new type of object, we need to define what it means for two of these objects to be equal. For instance, recall that when you learned about fractions, you learned how to identify whether two fractions were equal. Since the identifying information of a vector is its magnitude and direction, we define two vectors to be equal if they point in the same direction and have equal lengths. We often represent vectors graphically by arrows. In this picture, 4 vectors are represented. 2 of them are equal. Do you see which ones? Notice that U and W have equal lengths but point in different directions. U and M point in the same direction but have different lengths. Only U and V are equal. They point in the same direction and have the same length. The most basic interpretation of a vector is a displacement. For example, the displacement 3 miles south is a vector. It has both a magnitude, 3 miles, and a direction, south. However, other physical quantities can be expressed by a vector. A force acting on an object is a vector because the force pushes the object in a certain direction and with a certain strength. Furthermore, a velocity is a vector. It has both a direction of travel and a speed of travel, which measures its magnitude. On the other hand, a number, like 17, is not a vector. Numbers have magnitude, but 17 does not point in any direction. Similarly, the mass of an object has magnitude. Some objects are more massive than others, but this mass does not have any directional information to measure. A time is also not a vector, though there are plenty of ways to measure time. Finally, a location is not a vector. There is no direction or magnitude inherent in a location. This will be an important distinction, though, because the way we denote locations and vectors in mathematics turns out to be so similar. Speaking of notation, we should next discuss how we denote vectors. If we want to communicate to another person about a particular vector, how do we tell them which vector we are talking about? One notation is called endpoint notation. In endpoint notation, we take the point where the vector begins, in this case A, and the point where the vector ends, in this case B, and put an arrow over the names of those points. We call A the initial point and B the terminal point. We can use endpoints to determine whether two vectors are equal. Specifically, the following theorem states that two vectors are equal if their endpoints form a parallelogram. In this case, the vector AB is equal to the vector CD. Note that if the two vectors in question already lie on a line, then the parallelogram in question will be squished onto that line. Another way of denoting a vector is to quantify the displacement it represents. One way is coordinate notation. If a vector represents a displacement between 2 points in three-dimensional space, and we know the coordinates of those points, then we can measure how far the vector displaces in the x, y, and z directions. For example, if the point A equals 2, 3, 7, and B equals 5, 3, 6, then the vector AB displaces 3 in the x direction, increasing the x coordinate from 2 to 5. The vector displaces 0 in the y direction, as A and B have the same y coordinate. Finally, it displaces -1 in the z direction, as the z coordinate decreases from 7 to 6. We write that the vector AB equals 3, 0, -1. Notice that we can obtain the values in this notation by subtracting the coordinates of A from the coordinates of B. Notice also that we use these angle brackets to contain the coordinates. If we used parentheses, we might confuse our audience into thinking this vector is a point. Another way we indicate that we are discussing a vector is by our choice of names. Notice that when we aren't using endpoint notation, we generally name vectors with bold, lowercase letters, unlike points, which typically get capital letters. A theorem says that two vectors are equal if and only if their coordinates match in each component. Throughout this example, we assumed that our vector between 2 points lived in 3 space. However, we can also define displacements in spaces of any dimension. In the Cartesian plane, vectors will only have 2 components, one for x displacement and one for y displacement. Before we go any farther, we should address the similarity between the coordinate notation of a vector and a point. What is the difference between the point -5, 1, -4 and the vector -5, 1, -4? Well, a mathematician would say that these are 2 different types of objects, so by definition they are different. But that might not be a satisfying answer to you. Instead, notice that there is only one point, -4, 1, -5, 1, -4. It lives at a particular location in 3 space. On the other hand, there are many vectors, -5, 1, -4 in 3 space. They can begin at any point you like, but they are all mathematically equal to each other. The vector -1, 5, -4 that starts at the origin, however, seems special, not least because it ends at the point -1, -5, 1, -4. This vector is indeed special, and we give it a name. Given a point in the Cartesian coordinate system, the vector to that point from the origin is called its position vector. The components of a point match the components of its position vector. Think back again to the last time you learned about a new mathematical object, maybe fractions or functions. Once you defined what these things were, you next needed to define the mathematical operations you can perform with them. The word define is important here. There is no inherently correct way to add 2 fractions or to add 2 functions. These are operations that humans have defined that happen to make the most sense in the context that we use these objects. Similarly, with vectors, the mathematical operations on vectors are not a foregone conclusion. Instead, they are a set of rules that we agree to because they make the most sense and because they make vectors more useful. Given that, here is a definition. The sum of 2 vectors is denoted v plus u. It is calculated by positioning v and u head to tail. This means that the terminal point of v coincides with the initial point of u. Let's move u to make that happen now. The sum, v plus u, is the vector from the initial point of v to the terminal point of u that appeared here. You might be asking, could we do this the other way around, and would we get the same answer? Well, if we move u down here, and v over here, we can make the terminal point of u equal to the initial point of v. We still get a vector u plus v. If you look back, this vector is in a different position, but is equal to the vector u plus v that we got when we used the other order. We can also define the vector sum in terms of coordinate notation. We simply add the coordinates of each summand to compute the sum. In this case, the x-coordinates sum to 4, and the y-coordinates sum to 2. The vector v plus u is equal to 4, 2. The careful observer will note that we have just defined the same operation 2 different ways. We must be careful in mathematics not to logically contradict ourselves. But fortunately, these 2 definitions agree for all pairs of vectors. Both methods will produce the same answer. The second operation we will define is scalar multiplication. The word scalar is used to mean number in the context of vector operations. Here is the definition. Given a scalar lambda and a vector v, we can produce the scalar multiple lambda v, which is the vector that has the same direction as v but is lambda times as long. Here, as I change lambda, you see the vector lambda v does not change direction, but the length does change. For lambda less than 1, lambda v is shorter than v. On the other hand, if lambda is negative, then lambda v extends in the opposite direction from v. Whether two vectors point in the same direction or opposite vectors, we call them parallel. Scalar multiplication can be defined in terms of coordinates. We simply distribute the scalar to each coordinate and perform the multiplication there. In this case, 2.5 times the vector 6, 4 produces the vector 15, 10. 15 is 2.5 times 6, and 10 is 2.5 times 4. Let's look at an example of vector operations. We should be able to interpret this operation both visually and in terms of coordinates. Given diagrams of vectors u and v, how would we draw a diagram of 1/2 u plus v? Well, let's draw ourselves a vector u and a vector v. In order to add 1/2 u and v, we need a 1/2 u. 1/2 u should point in the same direction as u. It's a scalar multiple, but it should be scaled to be half as long. Here it is. Now, in order to compute the addition, we need to put these vectors head to tail. We'll take 1/2 u and draw another copy of its head at the tail of v. Here is 1/2 u. Where is the sum? Do you see it? The sum begins at the initial point of 1/2 u and ends at the terminal point of v. Here is 1/2 u plus v. If instead we are giving the coordinates of u, a, b, and the coordinates of v, how would we compute this? Well, first we can compute 1/2 u by distributing. 1/2 u is equal to 1/2 of a, 1/2 of b. If we want to add that to v, which is equal to c, d, we just combine the displacements in each component. The x component is 1/2 a plus c. The y component is 1/2 b plus d. Here's an exercise for you. Draw two pictures for yourself, u and v. How would you draw u minus v? Is there a natural place where this difference arises? Pause the video and try this yourself, and then I'll show you my solution. Okay, here's my solution. So I drew myself two vectors, u and v. In order to compute u minus v, I needed the vector minus v, which should be parallel to v, the same magnitude but in opposite direction. Here it is. Then I put u and negative v head to tail. Where was the vector u minus v? Well, in my case, it ended up here. Now, what is the significance of this vector? Well, you notice that if you turn that negative v around, you would just have v. So if we begin our vectors u and v at the same initial point, then u minus v would have traveled from the terminal point of v to the terminal point of u. That's a useful shortcut to know. We might get some use out of it. In case you think two notations is not enough, here's another one for you. This notation helps us put vectors in a more algebraic context. In the standard basis notation, we write a vector as the sum of scalar multiples of certain basis vectors. The basis vectors are named I, j, and in 3-space, we also use k. I represents a displacement of 1 unit in the x direction. J represents a displacement of 1 unit in the y direction, and k represents a displacement of 1 unit in the z direction. Notice these definitions will allow us to write any vector as an algebraic expression in I, j, and k. For example, the vector 3, 5, negative 2 can be written as 3i plus 5j minus 2k. You can check yourself that 3i plus 5j minus 2k gives the correct value by performing the 3 scalar multiplications and then adding the resulting vectors. When vectors are written in standard basis notation, vector addition looks like combining terms in algebra. Scalar multiplication looks like the distributive property. This makes it very intuitive to compute with. A vector has a magnitude and direction. The magnitude, at least, is something we can measure numerically. In the case of a displacement, it might be measured in miles. In the case of a velocity, miles per hour. Physicists measure force in terms of a unit called newtons. For any type of units, or for none at all, we have a formula to compute the length of a vector that represents a displacement of a units in the x direction, b units in the y direction, and c units in the z direction. We denote this length using absolute value bars around the name of the vector, and we calculate it using the distance formula. The magnitude of v is given by the square root of a squared plus b squared plus c squared. For an example, let's compute the magnitude of the vector 3, 5, negative 2. Well, applying our formula, we get that the magnitude of v is equal to the square root of 3 squared plus 5 squared plus negative 2 squared. All we need to do is to complete the arithmetic. This is the square root of 9 plus 25 plus 4. 9 plus 25 makes 34, plus another 4 makes 38, and so the magnitude of the vector v is the square root of 38 units. I want to define 2 more vocabulary words that will be important later. The first is a unit vector. We say that a vector is a unit vector if its magnitude is 1 unit. We will on occasion need to find the unit vector that points in a given direction. The following formula accomplishes that. Given a vector v, we multiply by 1 over the magnitude of v. Notice this is scalar multiplication because 1 over the magnitude of v is a number, and v is a vector. The resulting vector is parallel to v since it's a scalar multiple. It's also a unit vector since scalar multiplication resizes the length of the vector by that scalar. The other vocabulary we will define is the angle between 2 vectors. This is our best way of measuring direction. However, given 2 vectors floating out in space, it's likely that they do not intersect to form an angle in the classical geometric sense. Instead, we define the angle between 2 vectors to be the angle they would make if they were placed so that their initial points are the same. We use a special word for vectors whose angle is a right angle. We call them orthogonal. We don't call them perpendicular because they may not intersect. There's also a special word for vectors whose angles is 0 or pi. We've encountered that word already. Those vectors are called parallel. You may have gotten used to measuring negative angles or angles bigger than pi on the unit circle. In 3 dimensions, though, there's no good way to define whether an angle is clockwise or counterclockwise, so we revert to the geometric notion of an angle for vectors. Thus, the angle between 2 vectors is never negative, and it's never more than pi. That's all we have to say for now. Here are a few summary questions to help you review the important ideas of this lecture.